Thank you very much, Alain. I don't know if you will learn, but I'm a clinician, so it will be a clinical talk. And I wanted to tell you a bit about, or discuss with you, what is the link between the different disorders from a genetic point of view of neurodegeneration, what we see, what we mean when we say the disease has an onset, what is the onset, and how could we, if we were able to, treat in the pre-symptomatic phase of these disorders. And I will take several examples, and I hope that you're gonna enjoy discussing with me afterwards. So if we imagine then, if we say a neurodegenerative disease, if it's a genetic linked disorders, because I'm the geneticist, so I will only speak about those. If we think about this, we know that the persons at risk or carrier, they have their mutations since birth. So when do we expect to have a pathological onset? Immediately, a little bit afterwards, or only when the clinical presentation gonna start? I don't think so. I think when we come in here as a clinician, or when you see in animal models, I think we arrive after the battle somehow. So, and all this time where we could do something, either in treatment or to analyze the disease and to pick up some not disease-related or not disease-reflecting, but other markers that could show us how the pathological things are part of the picture being there, then we could really gain some time. If you think about Huntington's disease, where the carrier at age will start the disease perhaps at 50, I think it's really interesting to see. Parkinson's is even later, Alzheimer's is even later. So I think this phase is the most important one, and I want to speak about those. Compensation, I don't know why I put it in the title, because I don't have many examples about compensation, what's happening there, but we think there must be compensation. So what do these disorders have in common? And I think the most evident thing, they're all protein misfolding disorders with inclusions, intranuclear for the most, or intercytoplasmic one, and they accumulate a protein, which is most of the time hyperphosphorylated. If we think about what is accumulating, and if we put the disease over there, then we have the leading field for the tauopathy of Alzheimer's disease, alpha-synucleinopathy, Parkinson's disease, but also very early onset, more pediatric diseases like the NBIAs or the metal accumulation in the striatum. Then from the polyglutamine disease disorders, very interesting because you have Huntington's disease and all the other which are declined here, and the TDP43 with the frontotemporal dementias. What they all have in common is cognitive deficits, dementia. They all have them in a more or less pronounced manner. Can be in the beginning of the disease or can be later, but they all have this. So when we look at those, what do they have in common which we could pick up to say there is something we would target in different things? So the phenotypes are really overlapping. And what we did, for example, just to take Huntington's disease, there's one major gene. So you have 80% of, or 80 or 90% of the patients, they all have the same mutation. But if you take the clinical, if you come in with the clinical diagnosis of Huntington's disease, you will have some of those which look like Huntington's disease exactly, and this was done by people who know what they're doing. You still have some, they have Huntington's without the mutation. So if you analyze them again, and this was the work of Louis Mariani who did this, you can find some other reasons to have Huntington's disease, and another gene, the most frequent gene involved in disease is junctophyllin 3, okay? But then you still stick with 23 phencopies, which you don't know what they are. And when you follow them and look how they evolve over time, they have some different clinical outcomes, more cerebellar or even motor neuron disease. And then when we did a gene panel analysis in these patients, we found a gene or two genes at least which are completely responsible for frontotemporal dementia. So you see that even if you have a clear clinical phenotype which looks like Huntington's disease, you have the overlapping phenotypes in all these protein misfolding disorders. And I think this is important to keep in mind for later things. The other thing is that even from a genetic point of view, you can have the same gene being involved in a lot of different diseases from this same group. So if you take SCAR2, for example, which is responsible for one of the polyglutamine ataxias, and it has also a CAG repeat expansion, which is polymorphic in the normal population, but very well conserved, usually between 22 and 23 repeats and not more, and it's interrupted. So that's normal, what you all have in 2 copies. It was shown that if you have still normal, still interrupted with the CAA, but a bit larger than what you expect usually to see 22, your risk to have a motor neuron disease later in life is a lot larger. And this was a paper of this group in Nature in 2010, who wanted to look at the relationship between TDP43 and ataxin-2. That was their first idea, but then when they saw this relationship was really close, they looked at patients, 1,000 with amyotrophic lateral sclerosis, and you can see that there was a real difference in the ataxin-2 repeat length, still interrupted, still normal, not abnormal, in the group who has motor neuron disease. So it's perhaps today, ataxin-2 is the most frequent risk factor for motor neuron disease out there. And even more interestingly, I think, is that when the disease, when the expansion is too large, above 34, then you get cerebral ataxia. But not always, because it has been seen that in some families with Parkinson's disease, when you have a large CAG repeat, you get complete Parkinson's disease without cerebral ataxia due to this gene. And what's the difference? In the Parkinson's disease families with this expansion, the CAG repeat is still interrupted, like in the normal one, and it's pure CAG repeat in cerebral ataxia. So it's also true for Parkinson's disease that perhaps the most evident gene involved in familial Parkinson's disease today is ataxin-2, a gene which is usually responsible for cerebral ataxias. And if you have really large expansions, but a pure one, not interrupted, then you have even a phenotype which looks like Huntington's disease. So I think it's important to see that this kind of overlapping even of the course of the disease has to give us some hints how to interpret the clinical and the molecular features of the disease. And if you take a new gene, which is even more interesting because it's also repeat, only discovered in 2011, which was something we never expected because all the repeat expansion genes for the neurodegenerative diseases were discovered in the 1990s, between 92 and 96. And this repeat is a very frequent one responsible for FTDL and for motor neuron disease. And you can see at the figures here, which we were really all very much astonished if you see that this repeat is responsible for 65% of the familial disorder associating dementia and motor neuron disease. But even in only motor neuron disease, you have 44% which are responsible for this gene. So meaning, if someone has motor neuron disease without even a familial history, there is about 20% risk that they're carrying a gene which is responsible for a dominant disease. So this was a real new thing. But what I wanted to tell you about this, that when you look at ataxin-2 in these cohorts, and they are very small figures, but still it's interesting to see if there is someone with FTD or ALS or both carrying at the same time this repeat in C9 or IF72 and ataxin-2 intermediate expansion, so still normal, as I showed you for the risk for motor neuron disease, then you will have a motor neuron disease phenotype. Because we didn't understand before why this same mutation gives rise to amyotrophic lateral sclerosis, nothing to do really with dementia, or a complete dementia phenotype. So no, perhaps it's the ataxin-2 gene who gives this, or is the major modifier of the expansion in the C9orf72. So if we go into Huntington's disease again, and we're going to hear about this a lot today, I think, it's interesting to see that there we thought, at least, it's a disease which is quite a model one, because you have a major mutation, the CAG repeat here. It's polymorphic in the population that we know about. It's expanded, and you have a girl over there who died now, but what you can see when she's walking, that she has chorea because she's moving much. But at this time of the video, what you see here, she was already completely mute. She couldn't talk she couldn't talk anymore, and she was not able to take care about her life. You can see that when she was sitting there, that she tries to able to, control her movements when she sits down. You can see this now, sorry. So she has very diffuse movements, so she can control, she's closing her mouth because otherwise she has too many movements in the face, and she do this. But this is not the only symptom of Huntington's disease, and as I showed you before, the overlap is big because the most important sign of Huntington's disease is the cognitive decline. And this is due to this very tremendous atrophy in the striatum, as you can see here in postmortem, where the striatum are completely disappeared after the disease went on for 20 or 30 years. So why would this be a disease model? For several reasons: to test medication, or at least to approach the pre-symptomatic phase. First of all, because among the rare diseases, it has an incidence which is higher than previously thought. And this is a study we did with Sandrine Imbert, where we tested this gene in a population, nothing to do with Huntington's disease, because the 1 in 5,000 was done in population screened for Huntington's disease. But now we know it's 10-fold higher, probably, if you take a population which is not linked to Huntington's disease. So this was a very surprising finding. This very long pre-symptomatic phase before the disease starts means what's happening for people doing their protein accumulation during their whole life, but having no single sign, or perhaps do they have signs, but at least not obvious ones. And more interestingly, because if you want to work on Parkinson or other diseases, here in Huntington's you have the complete age-dependent penetrance, which means if you have an expanded CAG repeat in your gene, you're gonna have clinical signs at one point in your life. And perhaps more importantly for me, because this allows us to approach these people, it's that there is for a long time, since 92 or even before the 90s, a very well-established pre-symptomatic testing procedures, which allows people to ask for their genetic test and to even 20, 40, 50 years before they have onset know about their risk to develop the disease later on. So if you think, what do you need to get Huntington's disease at the end? You need the CAG repeat expanded, and you need to age. And then you have this pre-symptomatic phase. I don't really know what's happening there, but I'm going to tell you more about it. And you have this where a lot of people were thinking about the prodromal phase, where things start getting wrong. But it's a very difficult period to see if this is disease-related or it's not, especially in a disease where you have cognitive problems. Someone who's losing her keys, knowing that she's gonna have the disease later, will she think that this is the disease onset? Probably yes. You will think, if you would be a carrier, that if you do something wrong or spill your coffee, you're gonna start the disease. So it's difficult to assess this just before the disease becomes manifest. So I told you that predictive testing is a frequent request, and just to give you some figures, it's true that even if it's a long period here, which I show you just in our center at the Salpêtrière, but still we have 2,000 requests, let's say, and 82% are for Huntington's disease. All the others are later. I mean, the C9orf72 gene for the ALS and the motor neuron disease, it's like this now. So I see a lot of people coming in for this. So it will probably take over, but time is important for people being at risk. So what did we learn in 23 years of predictive testing? Can we reach these people? Can we treat them? Should we treat them? What should we do? We still know that even if the test is out there for more than 25 years, the uptake is really rare because only 15% of the at-risk patients take the test. So even if it's a more frequent disease, what we thought before, and even if we know the gene, and even if there are testing procedures out there, not all people will take the test, perhaps because there is no treatment. We know also that testing is not something we do without consequence. People are depressed after testing, whatever you do, and even long time afterwards, but independent of the result, if they are carrier or not. We can talk about this if you're interested. And the question is, does the fact to do testing, because that's a question people always ask you, does the test of knowing your status make you start the disease earlier? And this is true, because you can calculate the theoretical age at onset with the formula taking into account the age and the CAG repeat, because you have a correlation curve. And what we did is we looked at people did their test before 2008 and looked if they started the disease already. And you can see of this graph here that if you take in middle in the band here between the red or between the dotted lines, that is if your age at onset is falling into what you calculated. And this is earlier and this is later. You see most of the people start the disease earlier than what you calculate when they know about the disease. So their fear of people doing the test and telling me, but if I know about my status, will I start the disease before? I think they're right, or the Langbein formula is wrong, which is probably the case, because when you look at in a retrospective manner in a lot of patients where you assess their age at onset retrospectively, you find the same thing. So it's not that we are not able, or that the test, biologically it would be really weird, but that the test will start early if you know about it, but it's still that we are unable to assess the first onset of the disease, really. And if you ask those who did this study with us, if you say, you examine them, and there were affected ones and unaffected ones, based on motor examination, which is only one thing. But if you ask them, do you perceive yourself as affected? When they clearly are, here in this column, they're only 1/3 say, yes, I am, which is interesting. And 6% of those saying they're clearly not affected from the clinical point of view, they say, yes, I am. So both groups are paying a lot more attention to their signs. So this is really a problem because they don't perceive themselves as being affected, or if they do, they're wrong, perhaps they're not affected. And we are not able to say this either because it's very difficult to see if there are small signs. So what is age at onset? We all know, and this was completely overstated for so long, and there was one paper in 2012 who get the things quite straight, because we took 4,000 individuals with HD from all the networking people together to see what is the influence on age at onset. Is it only the expanded CAG repeat, or is it also the normal polymorphic repeat on your other allele whom have influences? So what you can see here, it's clear that the expanded CAG repeat is a major player in your age at onset, because if you have large repeats, you start always before 20. If you have normal ones around 40, you start between 20 and 80, but on an individual base, very difficult, but it's still a very nice correlation. If you look at the normal repeat, there's no correlation at all. And even more importantly, I think, is when you look at homozygous or heterozygous composite who has two pathological expansion on their both chromosomes, it's the larger one who drives the age at onset. So it's a complete dominant disease, and the normal allele doesn't play a role. Okay. But what's about this variance you see for one CAG repeat? So if, and this is the first GWAS who was done on the same cohort of 4,000 HD people to assess this variation only. Meaning for a given CAG repeat to see what is varying in between. So the analysis was done with the residual age at onset in a very defined group of patients having 55 CAG repeats, but always with the retrospective assessed age at onset. And what did they found? One peak. Incredible for the GWAS. I don't know if there are many people doing genetics here, but I can tell you GWAS, I know only Alzheimer's disease where has one major peak on ApoE. And there was one with two independent effects, a bad one, making the age at onset earlier, and a good one, making them a little bit later. Which genes are in this region, I don't know, but there's going to be a run on it now to see which genes are responsible for this peak, which probably modifies the age at onset in these people. You could imagine also that there are the other genes with polyglutamine expansion. If we go back to what I said in the beginning, what is relationship between all those play a role? And we did a study where we looked this time at ataxia patients to see if the longer or the smaller or the medium in between of the two expansions play a role in the age at onset in this cohort. Just to see about I just put the HD gene here. If you look at patients with SCAR1, SCAR2, SCAR3, and other polyglutamine diseases, the distribution is quite the same. But it was shown that the shorter allele of HTT influences the age at onset in SCAR3. I don't know what to do with it, but that's what came out of this. So perhaps when the normal allele, it doesn't have an influence on this in trans, on the HTT, but it has an influence on other polyglutamine disease. So to come to the real pre-symptomatic phase, because people working with pre-symptomatic carriers, like Sarah Tabrizi in London and Raymond Ross in Leiden and Blair Levitt in Vancouver and myself, we put a study up following pre-symptomatic carriers. So we had controls, which were intrafamilial controls, importantly, pre-manifest, and I'm going to speak mostly about those, and patients. And the most important thing we found in all this study, where we included a lot of different tasks to be able to pick up something which is happening before the disease starts, the only thing what we saw, and it was major, was the reduction of the brain volume, especially of the caudate. And if you look here, the green one are you. We are all losing brain throughout our life, and quite fast, because this is 1 year, 2 years, 3 years. So it's quite steep. I was astonished. And if you take the pre-symptomatic carriers, which are blue and violet here, they're losing brain faster, clearly, without having any clinical sign. A lot more the patients, but if you look only at the blue, it's quite impressive. And the caudate volume, it's tremendously atrophic 20 years before onset. And if you look at this here in this film, this is the caudate which you have, this is a region where you have to look. And if you see this, how this evolves over time, I take you through like this. You see that it's shrinking quite a lot. From 2008 to 2012. I do it again. 2008, wow, nothing left. Even more astonishing for me, at least, because we didn't thought about this, is the change in white matter. What are the astrocytes doing there? If you think about, look at the same scheme we saw just before. The controls are losing a lot of white matter substance over their life. That's crazy. But the pre-symptomatics lose more. And the question is, what is happening there? And it would be really interesting to look more in this after a while. So as I said, despite this major changes in the caudate, there is no clinical phenotype. So it does not translate in the pre-symptomatic phase. Why? There are just two cognitive tests. If you take this one, which is very sensitive to change, even it's a very simple test, it doesn't show anything for 2 years. If you imagine a trial, taking these tests doesn't mean anything. Don't use them. I mean, you cannot use any clinical outcome in these patients for 1 year. Because if you would do a trial, you would do it in this time frame, not in this time frame. Nobody will do a trial in 4 years. So you will look at this and you don't see anything in these pre-symptomatic carriers. And then if you take people who know what they're doing, and in Matthias Pesigloni groups in our center, Stefan Palmieri said, so let's see if we can see something in a really difficult task about reward and punishment learning. I don't put the task up, it's too complicated to explain, but the punishment learning and the reward learning was not exactly the same in carriers. If you look just in the pre-symptomatic carriers here, which learned less good the task when they were punished, if you compare to a reward learning. And the conclusion was that the gradient of atrophy was more dorsal to ventral because it starts with the punishment learning and the reward learning is conserved for a long time. So there is a small phenotype. Could we use this phenotype in a trial? I don't know. It's a very difficult task. And the other thing is if you do functional MRI, and this was done by Fatma under the supervision of Stéphane Lérissi, you can see that if you look at functional MRI with the idea to see which parts of the brain are more connected than others in a resting state. So it's just activity of the brain at the resting and see where are the small worlds which are more demanding than others. You can see in controls that you have, if you look at the sensomotor circuits, that you have clear hubs here, that you lose in pre-symptomatics. You can see that you lost the 44 here. And over time, because it's 2008, 2009, and 2010, this hub disappears. And in patient, you have none hub anymore anyway. So there is clearly something happening which you could probably follow in pre-symptomatic carriers. And if you think about treating, Fanny Moschel, who did her thesis with me, we started a long time ago to be interested in this energy deficit in HD, because perhaps it would be really interesting to target this in a pre-symptomatic phase of the disease. So the hypothesis was that there was a clear ATP loss in the animal models of the disease when they were killed by microwave and the ATP was looked by HPLC. You can see here the wild type and the R62 mice, and there's clear something already at 8 weeks. Why did we do this? Because we saw in pre-symptomatic clinic, when Fanny was still internship, that pre-symptomatic carriers were losing weight very early, without moving, without having any signs of the disease, but they were losing weight, and they were not depressed, and they were eating a lot. So when we did this analysis, we saw that there were an abnormal use of branched amino acids in the group of Huntington's disease, and we thought this would reflect an abnormal mitochondrial oxidation of these amino acids, and probably because there's not enough substrate in the Krebs cycle, we would be able, with a treatment, with an anapleretic treatment, to boost up the Krebs cycle. So how could we do a readout for this treatment? At the time, there was only MRI spectroscopy to measure a pH and creatine rephosphorylation, which reflects the ATP production in the muscle. So we did this in the muscle, and you can see that there was, in patient where was an abnormal rephosphorylation creatine in the muscle, in the legs of the people, they were improving with the treatment. So this was a very short study in 1 month, and we thought, that's great, let's do it better. And we put up functional spectroscopy in the brain, because that's where the disease is happening. It took some time to figure out what was the readout we wanted to look at, the ratio between inorganic phosphate and phosphocreatine. And this is the work of Isaac, who showed that this marker, if you do it in controls, because you register activity in the brain, you can see that there is a rest phase, an activation phase, and a recovery phase, which you don't have in patients and which you don't have in pre-symptomatics. So this is flat, and this is stable over time. If you give the treatment, restore this pattern of activation, rest, and recovery. So we're going to do a trial in September. We want to do it in April, but we do it in September because we have a beautiful administrative blockage in France, so we do it in September. But we will do it, and in pre-symptomatics. And just to finish, I would show you how difficult it is and why we're doing all this to find a marker which should be at least pathologically related, not disease related perhaps, to calculate the sample of a trial, the sample size of patients you should include in a trial. Or even for mice, you should ask yourself things like this, because we calculate effect sizes for things we look. And usually an effect size, if you take the gold standard, Parkinson's disease, UPDRS, in Huntington's is this, UHDRS, it has an effect size of 0.5. Take 0.5, think about a treatment which would expectantly get you better 50%. You have to put in each arm of the trial 300 patients. This is impossible. It's impossible for rare diseases like this. And if you think, because most of the treatment, you would expect 25% of improvement with your treatment, not 50%, because usually it's even less than 25%. This is not even, don't do the trial. That's what I mean. If you take caudate atrophy, as I showed you, because the effect size is so enormous, even in 6 months or 1 year, with the effect size of 1.2, then it becomes interesting. Because if you think even about a treatment, you would expect 25% of amelioration. At least perhaps you're able to do it. If you speak with a statistician, perhaps you can put it down a little bit and have 100 patients in each arm. And this is doable. So I think you really have to be careful thinking about trials in general, and even if you have a clear biomarker, to integrate this in your thoughts. And I will finish here, and this is just the group I mentioned, all the people who did the work during the talk, but there's just the clinical group in Alexis Bri's lab in the ICM. And I would like to say thank you to José Feingold, because it's my mentor and I just lost him. And I miss him because I put the pre-symptomatic clinic in 91 up together with him, and I feel like an orphan a little bit. So thank you very much.